Thank you for attending the webinar. I'm going to present my PhD research on the Salton Seismic imaging project. My title is Continental Rifting and the Creation of New Crust in the Southern Trough, Southern California, and Northern Mexico. SSIP is funded by 4 programs at NSF, including Margins, ArtScope, NSF Marine Geology and Geophysics, NSF Geophysics, plus USGS Multi-Hazard Program. All the instrument and technical support were provided by Iris Pascal. Also, I want to acknowledge all my co-authors listed on the screen. The background photo is a volcano taken at the Southern Sea geothermal field. About 40 million years to 12 million years ago, a spheroidal plate subducted beneath the North American plate, shown here. And by 12 million years ago, the subduction ceased and the plate motion positioned into offshore transform faulting, also the rotation of transverse range block. And inboard, it is basin range style west to east extension over here. If you look at this, the Nevada was narrower before the extension, and now it's getting much wider. By 6 million years ago, the transform dominated extension jumped inboard into the Gulf and localized in the whole Gulf. This is present-day Gulf California. The plate boundary between North American plate and Pacific plate is shown by the thick black line, which is a series of transform faults and short rift segments. The plate motion is about 50 millimeter per year in a slightly different direction from the transform faults, which is known as oblique rifting. Sandred fault is in the north and is particularized in the south. The amount of extension along the whole Gulf is the same since 6 million years ago, which is about 270 kilometers. The only difference is the Southern Trough and Northern Gulf of California is covered by thick sediments of the Colorado River Delta, while in the south there are no sediments. And the oceanic superspreading is only observed in the south, but not in the north. The question I want to address is, how does rapid sedimentation affect rifting process in the north? And the study area is Southern Trough, shown by the purple box. In the Southern Trough, plate boundary transform faults, sandred faults, imperial fault, and cerebral fault create a rift basin, including Coachella Valley, Salton Sea, which is a shallow water lake, Imperial Valley, and Mexicali Valley. The motion along sandred fault is 2.6 centimeter per year currently, and the motion along imperial fault is 3.5 centimeter per year. Some of the imperial fault motion position is transferred into San Jacinto fault zone to the west. Colorado River, shown in blue, carried a lot of sediment from Colorado Plateau into this basin. And the map view to the right side shown the Southern Trough and Northern Gulf California is part of the Colorado River Delta system. 5 little quaternary volcanoes are located at the southern shore of Salton Sea, which is named by Salton Buttes. Between Sandred Fault and the Imperial Fault, abundant seismicity occur at very shallow depths, shown by the black dots in the map to the right. The heat flow in the entire valley very high. On average, the heat flow is 125 milliwatt per square meter, which is more than double of the normal continental heat flow. And the extremely high heat flow is observed in the localized geothermal field, including Southern Sea geothermal field at Southern Shore Southern Sea, and also Bordy geothermal field in the middle of the valley. The photo on the right shows a volcano in the geothermal field, which are typically 1 to 2 meter high with a continuous degassing process. Salton Seismic Imaging Project is a coordinated project with 3 components. SSIP is onshore seismic refraction and reflection experiment, which is funded by NSF, Earthscope and Margin Program, also USGS. It has 7 lines in blue, also 2 3D grid in the Imperial Valley and in the Coachella Valley. All the red stars are our short point. Wet SSIP is marine seismic refraction and reflection experiment in the Salton Sea, which is funded by NSF Marine Geology and Geophysics Program. Yellow triangles are OBS location and the green line are airgun shots. Broadband SSIP is onshore broadband teleseismic experiment, which is funded by NSF Geophysics Program. All the broadband stations are shown by purple diamond along the east-west line. Along the east-west line near the US-Mexico border. For SSIP, there are 126 shots were fired at the source, with totally of 33,000 kilogram explosives. Most shot size is 115 kilogram explosive or 250 pound. The large shot is up to 1,040 kilogram explosive, which is sealed in a 43-meter deep hole with diameter of 20 centimeters. Those large shots are recorded by the Southern California Seismic Network as magnitude 2 earthquakes. All the recording instruments were provided by Iris Pascal. The top left shown is a single component geophone connected to a RF-125 or Texan. The geophone has a frequency of 4.5 Hz, and the Texan can keep recording for 3 days with a sampling rate of 4 milliseconds. The Texan is covered in a plastic bag and buried in the soil. We also use 3-component geophone shown here with north and east direction shown by arrows on the top. RT130 is used to record the data shown by the black box. Like a US transportable array, our instrument was picked up to download the data and then deploy it to the next selected site to record both inline and offline shots. So in total, over 2,700 land seismographs were deployed over 4,000 sites. In the Southern Sea, the airgun shot size is 3.44 liter, and they were fired over 2,300 locations. OBS are 3 components, 4.5 Hz seismograph and hydrophone. The sample rate is 5 milliseconds. They were deployed at the same time of SSIP to record both airgun shots and onshore shots. In total, 48 OBS were deployed at 78 sites. From January 2011 to June 2012, 42 broadband seismic stations were deployed at 5 km spacing along the east-west line by 16 personnel from 5 universities. Several of the broadband stations were deployed in thick sediment in the valley. As the larger broad impact, we have about 120 volunteers, including more than 50 students from 31 colleges and universities participated in the fieldwork in March 2011. The top left shown is our crew in the warehouse, and the bottom right are our geophone and Texans in the warehouse. The photo in the middle shows a technician from Iris Pascal training the students how to deploy geophones in the field. Bottom left shown student teams deploying and picking up instruments from the field. Here I show some data example of our shot gather. The shot point is represented by red star on the gather, also on the map in the bottom left, along the thick black line in the map. The horizontal axis is distance from shot to individual receivers, and each vertical trace represents one receiver. Vertical axis is the time for the seismic signal to travel from the shot point to individual receivers. And the inverse of the slope shows apparent velocity. The vertical axis is reduced by 6 km per second, so any apparent velocity of 6 km per second is flat on the map, on the data. We have slower sediment near the shot, also faster crystalline rock at offset greater than 10 km. You can see the transition from slow sediment to crystalline rock is very smooth, and there is no reflection at the boundary. We also observed basin reverberation or PPP arrival at a later arrival time. The gather is very symmetric on both sides of the shot, which indicates the structure inside the valley is mainly one-dimensional. Here is another data from the shot point near the Salton Sea along line 3 at the southern shore of Salton Sea. The bump at offset -20 is at Superstition Mountain, and the receiver in the west is more sparse than in the valley. We see slower sediment near the shot, faster crystalline rock in the farther offset. The transition between them is very smooth, and there is no reflection. The symmetric data along line 3 also suggesting a one-dimensional structure in the valley. On the left, the first arrival travel time picked from different shots along line 1 is shown by thin black lines, and the thick green line is a modeled travel time from our best fit 1D starting model, shown by green line on the right. We also have 1D starting model shown in blue for line 2 and red for line 3. Line 3 has slightly shallower crystalline rock than line 1 and line 2. From the starting model shown in last slide, we run travel time tomography to generate Imperial Valley upper crust velocity model along line 1, shown by the thick black line. It is about 65 km long from northwest to southeast, goes through Southern Sea geothermal field at the Southern Sea at southern shore Southern Sea, and the Brody seismic zone, Brody geothermal field, also all the way into U.S.-Mexico border in the southeast. All the red stars on the surface are our shot point. Vertical axis depth, the model is about 10 km deep. The color is our velocity. Here the color different from earthquake tomography. Cold color in blue shown is slow velocity, and the warm color is high velocity. As you can see, velocity smoothly increases with depth from 2 km per second soft sediment to about 6 km per second crystalline rock. And there are no sharp boundary between sediment and crystalline rock. Our shot points are very dense in the northern part of the valley, so we run a full inform inversion for this portion of the model. As we move back and forth, you can see the image from full inform inversion is very consistent with travel time tomography. And the high velocity is shallower in both Southern Sea geothermal field at offset or at a distance of 0, also in the Brody geothermal field at a distance 22 km. Here I show the velocity gradient from the velocity model. which is dv dz. Although there are no sharp transition for velocity, but the velocity gradient decreases sharply at about 3 km depths across the whole valley. And high velocity gradient is observed in two geothermal fields, Salton Sea geothermal field and Brody geothermal field at 22 km distance. In order to better understand the transition between sediment and basement, we built a synthetic velocity model by adding a 1 km per second velocity jump into the velocity model, shown at the bottom right. And the synthetic data gather has a reflection phase D pointed by the red arrow on the bottom left. However, this phase is not observed in our real data, which means there are no velocity jump as large as 1 km per second in the Imperial Valley. We also generate synthetic data from trial-time tomography and full-inform inversion velocity models to compare with the raw data. Here I show a raw data example. The short point at the short gather is in the northern part of the valley. Remember, we only use the first level, which is at the very top of the data, to run our tomography. And you can see this is synthetic data from trial-time tomography. And you can see not only the data matches the first level, it also matches the reverberation, which is PP or PPP phases correctly at the right time. I will move back and forth so you can see them. This is synthetic data from full-inform inversion. The synthetic data from full-inform inversion provides more details into the waveform, and it matches the waveform at a distance 10 to 15 km better than trial-time tomography. Here is the velocity model along line 2 in the Imperial Valley, shown by the thick black line in the map. The left is west and the right side is east. I label all the faults line 2 goes through on the top of the map, including Superstition Hill fault, Imperial fault, and Line 1 and Sand Hill fault. Our data and methods are not proper to identify those faults, but you can see them for comparison. Similar to Line 1, we have velocity increase smoothly from slow sediment with depths into a faster coastline rock. And the velocity gradient in the depths is slower than that in the surface. Also, you can see the basin in the west is slower and also deeper to the west of Line 1 or to the west of Imperial fault. Here I put the velocity profile from Line 1 model and Line 2 model together. As you can see, the velocity from Line 1 and Line 2 at the intersection of Line 1 and Line 2 is almost the same. And those results are from independent dataset and modeling. Here is a velocity model along line 3 in the Imperial Valley. The left is southwest, right side is northeast. We have Superstition Mountain fault, Superstition Hill fault in the west, also Salton Sea geothermal field at the distance about 42 km. Similarly, we have velocity smoothly increase with depths, and we have slower and deeper basin in the west at distance 15 to about 35 km. And the crystalline rock is very shallow beneath Salton Sea geothermal field, which is caused by high heat flow. The thick vertical black line is a state borehole in the penetrating to 3 km depths into the crystalline rock. We will compare our velocity model with the borehole measurement in this well in later slides. Patricia Prasad built a 3D velocity model for the Imperial Valley, shown shown on the left. She used all the currently available data, including SSIP data, which are 3D grid data, inline 3 seismic line, both recording both inline and offline shots, and 1979 active source impairment data by Gary Fries in USGS. Also, Southern California Seismic Network recording of both shallow earthquakes in the valley and SSIP shots. At 5 km depths, you can see 2 high-velocity zones at the Salton Sea geothermal field, also in the Brody geothermal field. And there are 2 low-velocity zones in the west side of the basin, which is consistent with the results I show along line 2 and line 3. Earthquake relocation using this new velocity model shows no significant change for both earthquake depths and also location. The borehole shown by red, yellow triangle in the map is about 300 meters from our seismic line. This borehole sees progressive metamorphism of sediment from surface into chloride calcite zone, biotite zone, all the way into clinopyroxene zone. And the temperature in the borehole is very high, up to 300 degrees C at only 1.5 kilometer depth. Green schist faces with mineral epidote is observed at 900 meter depth, where temperature is about 240 degrees C. And amphibolite faces is observed at 3 km depth, where temperature is about 350 degrees C. So the upper crust in the Imperial Valley is metamorphosed in young sediment by high heat and fluid. We also compare our velocity model with the borehole measurement. The green line is from this study, and the blue line is vertical seismic profile. Red line is sonic waveform logs, and the orange squares are measurement on the rock samples. As you can see, our velocity model is consistent with the borehole measurement. Our velocity gradient show a high velocity gradient zone shallower than 1.5 kilometer and a low velocity gradient zone deeper than 2 kilometer. The borehole data show the porosity decreasing from 25% to about 5% from 500 meter depth to 1.5 kilometer depth, and then the porosity stabilized at 5 to 10% in depth. So our high velocity gradient zone corresponding to the closing of porosity from 25% to about 5%. Here I plot the earthquake within 5 kilometers from our seismic line into the model. Line 3 is along the southern shore, Salton Sea. Line 1 it goes through the Imperial Valley in plane motion direction. The green line marks the porosity of 5 to 10%, and the red line is the velocity contour of 5.1 km per second. Blue line is velocity contour of 6.0 km per second. As you can see, most earthquakes occur in low porosity, which is about 5 to 10%, met sedimentary rocks with P-wave velocity greater than 5.1 km per second. Now let's look at some data containing the rifting structure at greater depths. This short point is at U.S.-Mexico border, shown in the map along the thick black line, which is along the whole line, including Coachella Valley, Salton Sea, Imperial Valley, and the Mexicali Valley. Left is northwest, right is southeast. The time reduced by 7 km per second, so any apparent velocity of 7 km per second will be flat. At offset negative 120 to about 65, you can see the recording is more sparse, which is OBS recording in the Salton Sea. Coachella Valley in the west, in the left, has bigger noise, so we only have recording near the shoreline. We observe mantle reflection PMP at offset greater than 40 km, and we observe mantle refraction at offset greater than 17 km. Those reflection and refraction at very short offset indicating a very thin crust in the Imperial Valley. This is the short gather for a short point at the northern shore of the Southern Sea, shown by the red star in the map. As you can see, we have very slow sediment, but the transition into crystalline rock is very sharp. And the crystalline rock velocity is almost constant to the left, which is to the northwest. This suggests there is a faster crystalline rock in the Coachella Valley, and the sediment is thinner compared to the central southern trough. To the right or to the southeast, Morhole reflection is at about 4 second time, and we see a Morhole reflection multiple in greater depths. The Morhole reflection to the north in the Coachella Valley is greater than 4 seconds. This suggests there is a thicker crust in the Coachella Valley than in the Imperial Valley. Using all the force arrival and PMP, PN, we build our velocity model in the plate motion direction shown by the thick black line. It is about 240 km long from northwest on the left to southeast on the right, including Coachella Valley, Salton Sea, Imperial Valley, and Mexicali Valley. All the red stars are our short points, and the green circles are OBS in the Salton Sea. Broadly seismic zone and the Southern Sea geothermal field are at the middle. We have velocity increase from slow sediment of 2 km per second into crystalline rock of 6 km per second, and all the way into the pink color mantle, upper mantle. The sediment in the Coachella Valley is thinner than that in the Southern Sea and the Imperial Valley. And we have thicker crust in the Coachella Valley. We observe a reflection at similar depths to the Morhole in the Imperial Valley in the Mexicali Valley, shown by the blue line. However, the PN from short points at the southern end of our model suggests the velocity beneath the reflector is slower than 7, so it cannot be real mantle, and the real mantle has to be 5 km, at least 5 km deeper than this reflector. Here I show the recoverage, which is the top panel is first arrival and the PN. The bottom panel is Morhole reflection PMP. As you can see, we have very dense recoverage for the whole model space. We build our upper crust and middle crust from first arrival travel times, and then we fix our upper crust and middle crust. We use PMP to model the lower crust and the Morhole depths. After that, we fix the Morhole depths and then use PN to model the upper mantle velocity. In the Southern Sea, OBS airgun data provide constraints for the upper crust, which enable us to better image the lower crust. In the central southern trough, we observe a very thin crust, which is about 17.5 km, and the Morhole is very flat. It is about 100 km wide in the plate motion direction. The velocity in the lower crust is homogeneously 6.8 km per second. The upper mantle velocity is uniformly 7.8 to 7.9 km per second. This means the upper mantle is very hot with partial melting, and the lower crust is mainly gabbros by underplating magmatism. We did a very simple geological interpretation on the velocity model. The thicker and the slower crust on both sides are all the continents. And in the central southern trough, we have sediment shown by yellow and the metamorphosed sediment shown by green, also gabbros shown by the red, and hot mantle shown by the pink. The middle crust in the central southern trough could be either be stretched continent or metamorphosed sediment, or it could be a mixture of The old continental lithosphere has almost rifted apart, but no seafloor spreading is observed in the southern trough. About 100 km wide new crust had been created by sedimentation and metamorphism from the top and magmatism from below in last 2 to 4 million years. Our collaborators Shuhar Barak and Simon Klemperer analyzed the entropy in the upper mantle along the east-west line using broadband stations. As you can see, the fast polarization direction is parallel to former Ferron subduction in the peninsular ranges, and they quickly change direction to along San Andreas Fault shear direction or extension direction beneath the southern trough and the Chocolate Mountains. This means the PV velocity in the upper mantle in the east-west direction may be even slower than 7.8 to 7.9 km per second in the southern trough. Here, the red dots are earthquakes within 5 km of our seismic line. As you can see, they are mainly in the green metamorphosed sediment and localized in a 30 km wide region. So, oblique body seismic zone suggests a localized brittle deformation in the upper crust, which occurs mainly in the new metamorph sedimentary rock. And the 1D lower crust, borehole, and upper mantle structure suggest the magmatism is distributed and the deformation is broadly distributed ductile deformation. In order to better understand the rifting process, we build a kinematic and thermal model from the current crust. On the left, we assume a 1D 3-layer crust with sediment and metamorphosed sediment of 8 km and a pre-existing crust, continental crust of 4.5 km and a gabbros of 5 km thick. We assume constant temperature of basalt solidus at the borehole to represent the partial melting in the upper mantle. Uniform extension will send the crust from black box into the blue dash box, and the red arrows shows the trajectory of particle motion. So the upper crust move downward and also to the side during tension, and the lower crust move upward and also to the side. The extension is at San Andreas Fault rate. In the meantime, we add sedimentation at the top in yellow, also magmatism at the bottom in red, at the ratio observed in the current seismic structure. The heat is transferred by both conduction, also advection, shown by the red arrows. From current seismic, from current crust structure, for any given rifting rate and magma generation rate, we could work backward in time to get the initial condition. In this case, we get a 27 km thick old crust, which is about 17 km wide. That's our initial time equal to 0. Then we run forward modeling to get crust thickness evolution, also the model the temperature. As you can see, the crust sinks very quickly in the first 1 million years, and then it stabilized at the thickness stabilized at about 17 km thick. So a reasonable sedimentation and magmatism could maintain the crust thickness. At the bottom right, the green line is our model temperature, and the red dashed line is temperature corresponding to the measured heat flow. As you can see, the slope is very consistent near the surface. So our model temperature is consistent with observed heat flow. Using model temperature and the composition of the crust, we can calculate a yield strength profile for the crust rheology. As you can see, our model rheology predicts the observed shallow brittle ductile transition shown by the earthquake depths. In conclusion, North American continental lithosphere has almost rifted apart, but there no seafloor spreading is observed. About 100 km wide new crust had been created by sedimentation and magmorphism from the top and magmatism from the below, which will become future continental margin if the Salton rift succeeds in the future. Rapid sedimentation keeps the crust thick and ductile, which delays crustal breakup and the initiation of seafloor spreading in the Southern Trough and Northern Gulf of California. For large late-stage rifts, it's very common for large rivers flowing into them, and usually they have very high heat flow. If the sediment is thicker than 4 km, metamorphism or sediment is very possible. This probably is a common process which builds new felsic continental margin crust. This new crust is geophysically similar to stretched continents, which means it may be unrecognized when interpreting passive margins. This process also delays final breakup and seafloor spreading. Thank you.
All right, thank you very much, Liang. That was a wonderful, wonderful talk. I did have a few questions come in while you were speaking. For those of you out there, if you have additional questions, please feel free to send those to me now, and I will happily put them to our speaker. The first question I had here is asking about the depth of earthquakes relative to the thickness of the crust. Yeah, this plot that you showed right at the end here, where you had the earth. Yeah, okay. So the question says, you suggested very thin crust in the Imperial Valley. Can you reconcile this with the deep depths of historic earthquakes on the Imperial Fault? And I don't know if maybe you had earlier, had you said that the crust was maybe only 4 to 5 kilometers thick there?
17 to 18 kilometers thick.
In the Imperial Valley?
Yeah.
Okay, so I guess then the earthquakes that you're showing on this plot here that fall below the metasediment in the stretched continent, or are those, or even deeper in the mantle sections, do you explain those as mislocated events?
I think if they occur in the lower crust upper mantle, they either be mislocated or it's a bigger event. Also, the earthquakes in the middle crust, in the stretched continent or metasediment, you can if at location 140 to 160, they are mainly deeper along imperial faults. Mm-hmm. So they are along a major plate boundary transform faults rather than shallower sand misty. For those sand misty at a distance 120 to 140, the deeper one is from the recent Brody swarm in 2012. That one goes deeper, but usually the smaller one goes shallower.
Okay, great. We've got a couple other questions here. Question here, it says, do you have explanations on the high velocities observed in geothermal regions?
Yes. In the geothermal field, because you will have more heat and more fluid flow, that will create more intense metamorphism, which will create high velocity crystalline rock in shallower depths.
Okay. All right, a few more questions coming in here. It says, can you resolve any potential signal of anisotropy in the stretched pre-existing crust?
Resolve the structure. We have, let me move to that slide. Currently, we can only image the velocity in that layer, and our constraint for that layer is lower than either near surface or deeper, because if we look at our ray coverage, that's near the bottom of our ray coverage, we only know the PV velocity. We don't have 3 components. So, but the data is available along line 2. If we have a model for line 2 in the future, we may be able to compare the velocity in different directions. But for my model, we cannot.
Okay. Question here about differences with the UCVM SKEC model latest version. I'm not sure if you could say anything on that.
Do you mean these slides?
I guess I'm not sure if that's the right. Let's see, Southern California. Oh, sorry, Southern California velocity model.
This the 3D imperial valley velocity model published in Geology 2016, using the Southern California community velocity model as starting model, but using more active source data to update the velocity. I think the velocity model is improved over the more simplified community model.
Okay.
But yeah, I don't know whether it's incorporated into the community model yet or not.
We had a question about the geophones used. So it says, are the 1 and 3 component geophones suitable for investigating also the deeper parts of the upper mantle, say 150 to 200 kilometers depth? I'm not sure if you have good good resolution that deep using the geophone data.
You mean the 3 component or single component?
Either or both.
The frequency of our geophones is 4.5 hertz, but it's capable to recording signal of 2 hertz. We see 2 hertz energy in our arrivals.
Okay.
So I think they can see at least deeper until the upper mantle, if you have very strong, very big explosive shots.
One big question here is if the San Andreas Fault extends south of Bombay Beach, or if the Imperial, I think this is the Imperial Mountain Fault, extends north of Brawley. Could you say something on that topic based on your work?
No, I can't.
So I think they're talking about kind of this this area in between where the southern terminus of the San Andreas and the northern terminus of the Imperial Fault.
Yeah, we don't know how far they extend from our model, but we interpret a Sand Hill fault which connecting which may be a paleo fault which is not active currently. We see that in our velocity model as the basin boundary faults. Let me show you. Like we have the Sand Hills fault at roughly the location of extension of Sand Jet fault as the basin boundary, but this is interpreted as paleo fault, which is not active. Our collaborator has one paper in revision to say about the deepening of Sand Jet fault from the seismic lines in the north in the Coachella Valley. In BSSA will coming out soon.
Okay, and one response here from John Hull regarding the Southern California velocity model. It says most of the changes from the Southern California community model occur at shallower depth, particularly basin structure. Our collaborators are currently incorporating this into the community model. And one other question here. It says, is there any possibility to use porosity estimations in the numerical modeling you performed?
In my simple numerical modeling, I didn't consider porosity because it is a uniform extension. The only effect of porosity could be considering the compaction of sediment. I didn't consider that impact in my model.
Okay, great. Well, if there's no more questions, I think we'll end it there. Once again, thank you very much to Dr. Liang Hong for this very interesting talk about a fascinating part of a plate boundary in Southern California. So thanks everybody for being here, and thank you to our speaker.